All right, welcome back everybody. In this video we are going to talk about stuff from section 4 of unit 4 of AP Calculus, Introduction to Related Rates. Start getting us ready for these related rates problems. So to lead into what we're doing here, I've got 3 paragraphs of kind of introduction here. So go ahead and think back to when we started learning about implicit differentiation. You know, when we were doing implicit differentiation, we could take the derivative of a function with respect to any variable that we wanted. As long as we applied the chain rule, no matter what we wanted to do, no matter what the equation was, we could take the derivative for any variable. So like if we had the equation r squared plus 2 sine of theta minus theta squared equals 5, we might have taken the derivative of this with respect to r, or maybe we might have taken the derivative with respect to theta. And that's kind of where we were back in those days. We might have taken the derivative with respect to either one of those two things. Something we didn't consider at the time was that we actually could have taken the derivative with respect to any variable that we might have chosen. And that's what we're going to do in related rates problems, is we're going to have equations set up like this, but instead of taking the derivative with respect to r or the derivative with respect to theta, we are going to take the derivative of those equations with respect to t. So let's start to look at what that looks like and how some of these problems go. And we're kind of building ourselves up to where we're going next, because it is one of what I would consider one of the tougher topics that students have in AP Calculus over the years. It's not super difficult, but it can get a little challenging at times. So let's go ahead, and in example 1, we're just going to go ahead and we're going to take the derivative of this function with respect to t, so that you can see what it's going to look like when we do a related rate problem. So I'm going to take the derivative of r squared with respect to t. I take the derivative of the outside, leaving the inside the same, that's 2r. And then I take the derivative of the inside, which is just r. The derivative of r, since we're differentiating with respect to t, is going to be dr dt. Then I've got a constant multiple 2, and I take the derivative of the sine of theta, derivative of the outside, leaving the inside the same, times the derivative of the inside. And in this case, the inside is theta, so I'm going to take the derivative of that with respect to t. That gives me d theta dt. And then I'm subtracting away, and now I take the derivative of theta squared, derivative of the outside, leaving the inside the same, and again, the inside here is theta, so the derivative, I'm going to take the derivative of that with respect to t, and then of course the derivative of 5, since it's a constant, is 0. And that's what it looks like if I take the derivative of that function with respect to t. Okay? Let's look at our next example, example 2. 2 cars are driving towards one another at a right-angled intersection, with one car approaching from the north and the other approaching from the east. Set up a relationship, then find an equation that shows the related rates of the vehicles with respect to time. So we have one car coming from the north and one car coming from the east, and they meet at a right-angled intersection. Well, the distance between the 2 cars, that bubbled a little bit, but that should be the hypotenuse of a right triangle there. If we call the one car A and the other B, we know that the distance between the 2 of them at any moment in time is c. So as these 2 cars drive closer and closer to the intersection, the values of A, B, and C are all changing as time goes by. But now we can develop a model that shows the relationship between the rates of the vehicles with respect to time. So I start with an equation with all of these variables contained, a squared, b squared, c squared. The most clear model that we can come up with here is using the Pythagorean theorem. And this is an equation that relates the variables a, b, and c. And then to relate the rates of those things, all I'm going to do is I'm going to take the derivative with respect to time. The derivative of a squared is 2a dA dt. The derivative of b squared is 2b dB dt. And the derivative of c squared is 2c dc dt. And so now I have an equation that relates the rates of those vehicles. The change in A with respect to time, that's how fast car A is approaching the intersection. The change of B with respect to time, dB dt, that's how fast car B is approaching the intersection with respect to time. And then, of course, dc dt is how fast the distance between the two cars is changing with respect to time. All right, let's go on to a little bit more on this topic. Come on, turn the page. All right, example 3. The radius, height, and volume of a right circular cylinder are related by the equation v equals pi r squared h. How is dv dt related to dh dt if r is constant? So if we have v equals pi r squared h, if r is constant, that makes all of this right here constant. So that's just a constant multiple. So when I take the derivative with respect to time, this becomes dv dt equals the constant times the derivative of h with respect to t, which is going to be dh dt. So that's the relationship between dv dt and dh dt if r is constant. We'll do the same thing, volume equals pi r squared h. Now we're looking for how dv dt is related to dr dt if h is constant. And so now my constants are pi and h. And so dv dt is going to be equal to the constant multiple pi h times the derivative of r squared with respect to time. And that's going to be, again, derivative of the outside leaving the inside the same, times the derivative of the inside, which, since we're taking it with respect to t, is dr dt. And so we end up with the equation that dv dt is equal to 2 pi hr dr dt. And that's the relationship between dv dt and dr dt if h is constant. Oh boy, part C. How is dv dt related to dr dt and dh dt if neither r nor h is constant? So we've got volume equals pi r squared h. So what's constant? Just the pi. So we're going to take the derivative of this with respect to time, gives us dv dt equals pi times, and now I'm going to take the derivative of r squared h. All right, sorry about that. I got a knock at my door, so a little of my train of thought has been interrupted here a little bit. So we've got the constant multiple pi out front here, and then we're going to take the derivative of r squared h with respect to time, and in order to do that, we're going to use the product rule. So we've got r squared times the derivative of h, which is dh dt, plus h times the derivative of r squared, which is 2r dr dt. Okay, and then from there, all I really want to do is, clean this up. I guess I can factor an r out of both of those terms, and it becomes pi r times r dh dt plus 2h dr dt. And there's a relationship that expresses the connection between dv dt, dh dt, and dr dt if none of the variables are constant. All right, last example here, example 4. An airplane is flying on a horizontal path that will take it directly over an observer. The airplane maintains a constant altitude. Relate the rates of change of the distance between the observer and the airplane and the horizontal distance between the two. Okay, so the distance between the observer and the airplane and the horizontal distance. So what we have here is, don't mind my drawing because my drawings are always terrible. We have observer and the airplane I'm not even going to draw an airplane because my airplane is going to be so terrible. The airplane maintains a constant altitude, so it's just cruising along in this direction. So we've got, let's see, we've got the constant altitude, we've got the horizontal path of the airplane, and then we've got the distance between the plane and the observer. And I just broke my number one rule, and you'll see in a minute why it's my number one rule for defining variables in related rates problems. Hopefully I'll never do it again, but I did it in this problem. So we've got that relationship, and that means, there's a right angle here between the altitude and the horizontal cruising distance of the plane. So that means, again, we have a Pythagorean relationship, a squared plus h squared equals d squared. And now we want to take the derivative of this with respect to time, but something that you want to keep in mind here, because the airplane's maintaining a constant altitude, no matter how far the airplane's flown along here, the value of a right here does not change. It's a constant. So when we take the derivative of this, we need to realize that a squared is a constant. And so when we take the derivative of that constant, it's 0. Now the derivative of h squared is 2h dh dt. And the derivative of d squared is 2d dd dt. And this is why I never use a lowercase d as a variable in a related rates problem, because to me it just gets too darn confusing, all these lowercase d's that show up in the dd dt. So I tend to avoid it. All right, folks, that was an introduction to related rates. You're going to do a little bit of practice with this material, and then we're going to come back and we are going to dig into related rates and how we solve them. So that's the end of section 4.4. Come on back for section 4.5 when we really dig in on related rates problems. Okay, have a great rest of your day, everybody, and we'll see you next time.